This is the ReaderWriterLock demo. In this demo, I will demonstrate the ReaderWriterLock and ReaderWriterLock Slim classes that are used for synchronization in .NET. Now, the ReaderWriterLock has to be one of my favorite synchronization techniques because it's extremely well suited for the producer-consumer model, where you have certain threads that want access to read data from a resource, and then you have other threads that want to write data or change the data on that resource. Now, with that particular setup, it makes sense that we would want a synchronization technique that would allow us to safely read as many items as we want, as long as the data that's being read from isn't currently being changed. Now, with the reader-writer lock, we can accomplish that quite easily, because when you enter a read lock, basically anything else that also wants a read lock, they can all team up together to read at the same time. However, when a thread requests a write lock, as soon as all the reading that is currently going on is done and all the readers have released their locks, then the writer lock will obtain a dedicated lock by itself so it can make changes. Then everything else that also requests a lock after that is queued up until that writer is done performing its actions. So for this example, I have two SafeStack classes. I have a SafeStack class and a SafeStack 2. If you were to look at both of them, you would notice that they're virtually identical, except the difference is in SafeStack, all of the calls to enter the locks will block until they obtain the lock. The SafeStack 2 class, however, employs a timeout. Like in this case, we have a 1,000 millisecond timeout to try to enter this upgradable read lock. So with SafeStack 2, we would time out if we do not acquire a lock in a given amount of time. Now, which approach you use is entirely up to the problem you're trying to solve. In most cases, if you do not have long write blocks of code, in other words, any writes that occur are relatively short, you should probably just try to use the regular enter and exit commands, enter write lock or exit write lock, etc. However, if you have the possibility of your writes or reads taking an extraordinarily long time, in that case you probably want the ability to time out to at least notify the user that something's busy or something to that effect. Well, let's take a look at the code in SafeStack, and then we'll look at SafeStack 2, and I'll show you the differences. So in this class SafeStack, you can see here it is a generic, so it's going to create a stack of objects of type T. And again, because it's generic, we define T design time when we create a SafeStack object. Inside, we have our list of items of type T, and then I create a ReaderWriterLock Slim. Now, the difference between ReaderWriterLock Slim and ReaderWriterLock is just in how it implements its wait for the ability to acquire an exclusive lock. With the Slim, it basically is just going to enter a little loop in the background. Let's just say through 100,000 cycles. And it's just going to sit there and do a for loop and keep checking to see whether or not it still has not acquired the lock, or if it's going to still be waiting. If it takes too long in the Slim mode, where it's just basically in a wait state, it's going to be upgraded to a full reader-writer lock, in which case it's going to use more heavy objects behind the scenes while it's waiting to acquire and then release locks. So unless, like I was saying earlier, you have long-running reads and writes, the Slim version of the reader-writer lock is probably going to be better because it's lighter weight and will perform better, especially if you have many thousands or millions of operations occurring using this lock. Okay, let's take a look at pop. Like any standard stack class, pop means take the top element off of the stack. So if we have a stack of coins, you would always take the coin off the top, because if you took the bottom one, it would tip over the rest of the coins. So using that analogy, we would always take the top coin off of a coin stack. So first off, we create an item of type T called item, and we set it equal to the default value of type T. Remember, that is a technique you use with generics, because you can't assume it's nullable and you can't assume it's a value type. So this allows us to just set item to the default value of whatever data type T is. Then we enter this thing called upgradable read lock. Now the upgradable read lock allows us to enter as a read lock, but later on upgrade that same lock handle into a write lock. Now you might ask why we'd want to do that. Well, it's because we know if we enter a read lock, if there's another read that currently has the lock, we will be allowed to acquire the same lock right now without waiting. And since before we pop, we want to make sure there are items in the list to pop off of the stack, we want to read the count property from the list. Now, because count is a volatile property, in other words, it will change based on the number of items in the list, we want to make sure we read it in a safe manner. So that's why we enter using a read lock. In this case, like I said, upgradable read lock. So then we check to see what the count of the items are. And if there are more than 0 elements, then we attempt to enter the write lock. And notice here, to enter the write lock from an upgradable read lock just requires us to use the same lock object and just say enter write lock. Now, once that has occurred, we are in a write lock, so we are free to change items. In this case, we are going to retrieve the last item off of the list, and then we will remove that item. Once we are done removing it, we exit the write lock. Notice here we did that before the return. That is because returning the item does not affect the state of the collection or the M items list. So as soon as we are done manipulating the state of the item we're trying to protect, in this case M items, we exit the lock immediately, because write will block everything else. So we only enter the write lock and stay in the write lock as long as necessary to perform whatever operation we need to do. As soon as it's done, we get out. Then, since we're also done reading, we exit the upgradable read lock. And just like matching parentheses or matching curly braces, for every enter, there has to be a corresponding exit. In this case, enter upgradable read lock, there's a corresponding exit upgradable read lock. Enter write lock, exit write lock. And also note that it's usually not permitted to, like, say for instance, enter the upgradable read lock, then enter the write lock, and then exit the upgradable read lock followed by exit write lock. So all of the matching pairs of enters and exits have to match together, just like parentheses or curly braces. And then finally we return the item. So using the upgradable read lock isn't that hard. Okay, not going to be used all the time, but this is an example of where it would be useful, where a write may be the final thing we do with the protected resource, but we first start with a read to see if anything actually does need to be done. Now push is pretty straightforward. We don't need to enter an upgradable read lock, because with push it's arbitrary, doesn't matter what's in there, we're putting something in, so we're going to actually manipulate the data, so we have to enter a write lock, period. So we say mlock, enter write lock, then we add the item, which will put it at the end, then we exit the write lock. Peek, if you notice with peek, it's very similar to the pop, except the difference is we never make a change to the underlying data, so we don't ever have to get into a write lock, so we don't use, again, the upgradable read lock. So we say, again, create a default item of type T, mlock.enterReadLock. Once we've acquired the lock, We make sure that there are items in the list. If there are, we acquire it, we exit the read lock, and then we return the item. Now count is another one of those properties. As I mentioned, it is volatile. So it theoretically could be being manipulated at the time we query it. So rather than take a chance, I am going to put the count property inside of a read lock. Now notice here I changed the way I did things a little bit. Just to make sure that we always release a lock once we've acquired it, it's sometimes a good idea to put your code within a try block, not necessarily to catch an exception, but to guarantee we run this finally code. So we enter a read lock, return the number of items that were in the list, and then we always guarantee we'll release the read lock when we're done. So that's another technique you can use to guarantee that we don't have orphaned enters in our reader-writer lock. Because we always want to make sure for every read lock, we have a corresponding exit for that read lock. Now let's move over to SafeStack 2, which pretty much is accomplishing the exact same thing as SafeStack, but instead of using just enter, read locks, etc., we are going to use the try version of these methods. I'm going to start at the bottom, since that's the simplest method, the count, and then we'll work our way up to the more complex pop. So taking a look at count, you can see here we again try to enter a read lock using the try version of enter read lock, which requires us to pass in some timeout. Now you can pass in basically an infinite timeout here, but there's no reason to use that as opposed to just the enter read lock. So the only time you're going to use try enter read lock is if you do want to time out if we're not able to acquire the lock. So if we are able to acquire the lock, we want to make sure that we exit that lock. Notice there is no try exit read lock. We're just going to say exit read lock. Okay, so we return the items count. Finally will be triggered, which causes the exit read lock method to fire on the lock. If we were not able to acquire the lock, this method would return false, in which case we would not have processed what's inside the if block there, and then we'll throw a timeout exception. Now you can be more detailed with the message that's thrown from this timeout exception, but in this case it's pretty clear what it means. We tried to obtain the read lock, but we weren't able to. Now most of the time I do not like to hard code values like this within the code itself. Rather, I like to have in a settings file the actual timeout value for specific operations, maybe for all of your reader-writer locks or whatever methods you have that will also support timeouts, and store them in the settings file. That way you don't have to recompile if you notice that 1000 is causing a lot of timeout exceptions and you're willing to wait for 2000 milliseconds or 2 seconds. Then you can change it in the config file without having to recompile all of the code. Moving up, let's take a look at peek. Again, peek looks at the top item in the list, but it doesn't manipulate it. It just simply returns it. So we will start by creating a default T. Then again, we try to acquire the read lock. If we do acquire the read lock, we will execute this try block here, which is pretty identical to what we had previously. We check to make sure we actually have items in the list, and then we set item is equal to items.last. If we go back to SafeStack, you'll see the difference here is if it didn't exist, it simply returns the default of type T. With SafeStack 2, we're throwing an index out of range exception. Again, it's a preference thing, whether or not you want your data structure to throw an exception on failure or you want it to return a default value. If T happened to be something like the student class type, then it would return null if you return the default T. In this case, I'm going to throw an exception if there aren't any items in the list. And again, we use the try block so we can successfully exit the read lock once we have concluded with it. Push, pretty straightforward. We attempt to enter a write lock. Again, we're waiting 1 second. If we've acquired it, we add an item to the list, and then within the finally block, we say exit write lock. Moving up, take a look at pop. Again, we define a default item. Then we try to enter an upgradable read lock. Same syntax as all the other try versions of these methods. We're going to wait 1 second. And then if we manage to get in, we will enter this try block. And as you can see here, it terminates with a finally that allows us to exit the upgradable read lock. Then, once we've obtained the outer read lock, we check to see if we have any items in the list. If we do another try. This time, try enter write lock. Again, waiting a second. So theoretically, this method could be successful and still take 2 seconds to operate due to the fact that we have 2 waits in here for 1 second. Now, unless you're doing database calls or you're doing file reads off of a slow hard drive or something, waiting a second is probably going to be a lot longer than you'll ever have to wait. Okay, if you're manipulating an internal data structure like a list like we are here, that actually will happen very fast. We're talking microseconds. So waiting a whole second is probably a lot longer than you'll need to do. So we wait that second. If we acquire the write lock, we again enter another try block. This time we get the last item, then remove it. And finally, we say exit write lock and continue out. Okay. Notice here if the count of items is less than or basically 0, then we throw the index out of range exception again. So this is basically 2 different takes on the same data structure, both implementing a stack of generic type T, one using blocking calls in the reader-writer locks, and the other using timeout calls with the reader-writer lock. If we go to Program CS, you can see how we implement using these particular stacks. I've only shown in this example how to use safe stack without the safe stack 2. You could pretty much interchange it with safe stack 2 and get the same functionality. Okay, so we start by creating a safe stack of type int called stack. We create a thread called producer, which is equal to this method down here called producer thread, which we'll take a look at in a minute. And we start the producer thread. Then I create 4 consumer threads. So you can see here I say thread consumer equals new thread consumer thread. If you were to go down, you'll see that method here. And again, I'll look at that later. So we'll have 4 consumer threads all trying to consume what the producer thread is pushing out. Then we sleep for a second. Then while the stack.count is greater than 0, and remember this count property is part of the safe stack, so it allows us to do that in a thread safe manner. And we're also making sure the thread called producer is still alive. So while there's still something to process, or the producer is still alive, because with 4 consumers, we could basically consume all that the producers or the producer has produced, but it still has work to do, so the thread will still be running. So we want to make sure both of these conditions are false before we quit. So every time we get into this while loop, we just sleep for 1/10 of a second, and we keep doing that over and over again. Then I set mquit to true. Mquit to true is basically going to signal the consumer threads that it's time to turn off. Remember, we're going to sit here and wait until the producer thread is done. So we don't really need to signal the producer thread. It is basically going to complete its work. And then the thread will die, in which case is alive will be false. then it'll drop down here, setting mquit to true. So it's only going to signal the consumers. So let's take a look at producer thread. Notice here I create a stack called stack here. It's a safe stack events. Okay, and then I will push these objects or these ints into the stack. Okay, notice here I didn't actually create it here. It was passed in because this is a special type of thread start. Remember, it's going to be a parameterized thread start in this case. So we're saying start the thread, here's some state data. We're taking the stack that was created outside of the thread and converting it into this object here. So I'm backtracking on what I said a little earlier to make it less confusing. I apologize for that. But we have this for loop here for int I equals 0, I is less than 20, I plus equals 4. And at each step of the loop, we're going to push several items. And then we sleep for a half of a second. Okay, remember, every time we push, it's going to acquire a write lock. The consumer thread, pretty straightforward. It again is passed that stack object that was created outside of the thread, and it's simply waiting until mquit is true. While mquit is false, it checks to see if the count of the stack is greater than 0, and if it is greater than 0, we pop an item off of the list and show it to the console window. Then we sleep for some random amount of time between 1 and 3 seconds before going back to the loop, checking mquit, and reading the next item off of the queue or the stack. So running this code, you can see here we have the producer pushing items. It pushed all 19 items. And then the consumer popped all the items off. Okay, notice here it pushes 0 through 19 in order. And then we're having all of the items popped off. As you can see here, 19, 18, etc., etc., etc. But notice here the consumer started working before item 4 was pushed. So we had 4 consumers pulling items off of the stack almost immediately. So the stack had 4 items in it. 4 consumers were waiting. It consumed 4 of the items. Then the consumers went into a sleep state. We pushed several more items. And then 2 of the consumers woke up, 1 and 2. And then they pulled off 15 and 14, which were the last 2 items in the list. And then we pushed 4 more items. And then consumer 0, then 3 wake up, they pop off items. And then finally we get done popping off all of the available items. Once that's done, we set that mquit variable to true, in which case all of the consumers then signal we are quitting because we have monitored that the mquit variable has been set. Of course, we could do that with a manual or an automatic reset event to signal, but in this particular case, using a bool variable is pretty straightforward. So with a little bit of work, you could take this producer-consumer model that I used here in the SafeStack classes and adapt it to a wide variety of applications, such as file processing, where you want the ability to have several consumers and several producers. Maybe you have something monitoring different directories on your file system, and those will be the producers. And as a file is added to the file system, the producer will scan the file, maybe make note of the file name, and put that in a stack or a queue somewhere. And then the consumers, as you have as many threads as viable, will sit there waiting for an entry in this queue, and once the queue has an entry, it will consume that item, and then other consumers will be waiting in the wings to also consume the data. So in this case, we would be protecting a list of file names. Now that in itself is going to be short-lived locks, because we're not going to hold open a lock as we're processing the file. We're just holding open locks long enough to add a file to the list or remove a file name from the list. So the producers will put the file name in, the consumers will pull them out.